In this video, I'm going to share with you a live PLC programming workshop that one of our clients, Alikhan, was kind enough to share with us within our paid community. And this is a real-world project done in the Siemens tier portal that he then later used as a demonstration project to land himself a new role as an automation engineer just 12 weeks after joining us. And if you'd like to connect with Alikhan, I'll put his LinkedIn in the description below. Let's get into the video.
Now I will share my screen. So, can everybody see my screen?
Yeah, yeah.
Yeah. So, well, just for information, I'm not an expert, but a PLC enthusiast. Yeah, and I'm very open to any suggestions, recommendations, and opinions. So, because I'm pretty sure there are more experienced people than me here on the call. So, you're very welcome to share your opinions. Yeah. So first, I suggest we go over visualization part, maybe see how it works. We will just press the buttons, play with the temperatures, and we will see how the system responds. Then after this, we will go deep into the logic in detail and go through each network and see
Yeah.
how it works. Yeah.
I think what would be helpful as well, Alikhan, and
Mm.
maybe you're going to do this in a visualization, but kind of paint us a picture of what
Mm.
this project is
Oh
from a
yeah, yeah,
big overview
yeah,
standpoint.
yeah. Okay. So as you can see, there is a motor, and the motor has motor winding temperature. Yeah? So as you can see, we have three temperature transmitters, let's say. Yeah? So and they work in 2 out of 3 volting configuration. So what it means, if any two of them will reach the threshold, it will just trip the motor. So let me show you the the main block. So main block is kind of the environment where we program the all the logic. So here, as you can see, you see high alarm, yeah, for first transmitter. And that band to reset high alarm is 2% out of calibrated range. So let's suppose that our temperature transmitter operating range from 0 to 100, yeah. And to trigger high alarm, we need to have our temperature above 75 degree of Celsius, yeah. So it will just activate our high alarm. And in order to reset the high alarm, it should be less than 73 degree of Celsius, considering the 2% of calibrated range, right? Because 2% out of 100, it is 2, right? So it will just reset the high alarm. The same principle I did for the the same principle I did for the other two transmitters. As you can see, the same here also. And for high alarm, I also used the same principle, but the threshold value, trip point is 85.
Yeah.
And
So
mhm. Yeah.
so just so like we've got like these temperatures here, and we there's three alarms, two alarms.
There are two alarms for each temperature transmitter, high alarm and high alarm.
Yeah. So like temperatures, let's say we're just focusing on one temperature sensor.
Mm-hmm.
It's got your high alarm here, which is set to 85. We set that threshold to 85, and we got like the high alarm, which is 75.
Yes, correct. Yes.
So the temperature comes up, it goes past the 75, then it triggers that alarm.
Yes, here I will show you. For example, this one, yeah, transmitter 103. So it will just set the high alarm, yeah, when it reaches equal or greater than 75, it will
Yeah,
trigger the alarm, high
yeah.
alarm.
And then
So
if that temperature then so that's triggered, then if that temperature continues and then it goes up as high as the high alarm,
yes,
this 85 degrees, then it triggers that one as well.
correct, yes, correct.
Yeah. And
So
then as it comes down, it needs to go below. It's not going to reset if it gets to 85. It's going to get to 83 and then it resets and switches off
mhm.
on the high alarm. And then the high alarm, it goes to 73 and it switches off.
Correct, yes.
Yeah.
So, yes, as you said, high alarm will be reset below 83, and high alarm will be reset if it is below 73.
Yeah.
So, and when we have, as I already mentioned, we have a 2 out of 3 voting system, yeah, which means that if any two of them will reach, will be above 85 degree, it will trip the motor, yeah. So I will show
Right.
you the logic. As you can see, you see motor trip, yeah. So as you can see, we have a combination of two transmitters, like transmitter one, transmitter two, transmitter two, transmitter three, transmitter three, transmitter one. Yeah. So for example,
And
let's say
sorry to cut in. I just want to explain a little bit more detail. So these are like AND circuits. So we
correct.
need like the top one, M12.3 and M12.4. Like if they're both triggered, then that allows that rung to complete that circuit to go from all the way on the left through M12.3, M12.4, and then over to that motor trip over there. And it's the
Yes.
same thing with the temperature two. Yeah, those other ones there. So they're AND circuits. They need
Yes.
both of those to be true to then send the signal over to the right.
Correct. Yeah. So if we receive high alarm from any of them, yeah, it will activate. For example, let's say we receive high alarm from transmitter one, it will activate this one, right? It will be energized. Then if we receive from temperature transmitter two, it will also receive, and it will shoot the circuit, and it will activate motor trip. So, and I have a reset, yeah, to reset motor trip, to reset the trip. But you see, there is a thing. For example, if my high alarm is still active, yeah, I cannot reset. What I need to do, I need to lower the temperature below the threshold value of 85. Then I can reset my motor.
How
Because
do you reset that? Is that like are you where's that reset coming from?
which one? This one or for high alarm?
This one here.
This one, as you can see, so I will open the WinCC. You see this
Ah,
preset?
right,
It is linked to HMI.
right. So it's like a button basically.
Yes, yes,
Yeah,
correct. Yeah.
cool.
So then here our motor circuit itself, it is for start and stop the motor.
I'm
So
just gonna sorry
Mhm.
to keep butting in, Alikhan. Guys, just where we're up to at the moment. Does everyone kind of like does anyone have any questions on where we're up to at the moment?
I do. Is that reset a manual reset or can it be done remotely?
For this specific case, it is a, remote reset from HMI. Sorry, from maybe operation station, yeah, let's say. It's not a physical reset, it is a software button reset.
Thanks, Alikhan.
Yeah.
Yeah, so that could be positioned kind of like where the machine is, but like the motor might be over there, but where the operator would be. Or it could be like in a control room, at the end of the factory that you can access on a web page.
Yes,
So it's
correct.
yeah, it's a digital button that you can press. Yeah.
Yeah. So moving on to the next network, this is motor control circuit. So this is basically for starting and stopping the motor. But in order to start the motor, we need to have some permissive signals, right? To start the motor. So which is power on. So it means that, for example, we have main circuit breaker, yeah, coming to the motor to power up. So it will have like auxiliary contactor with a normally closed or normally open contact. So in this case, it is normally open. When we close the main circuit breaker, our normal open contact is no longer open; it is closed, and it will just supersede. So in here it is normally closed, right? But when we activate the main circuit breaker, it will receive the signal and it no longer closed. It will be open, and we will now receive no power alarm. But it will close here, and we will receive permissive signal to have motor available. You got my point? Is it clear? Uh,
Yeah. Yeah. So the no power alarm is just to say, look, like the MCB is in its off state,
yeah.
but
And mhm.
if it's so, and then if it's on its off state, nothing that like that motor available, you can't achieve that state.
Correct. Yes.
So it
Yes.
needs to be in its on position to have, yeah, that rung of power on, and then you've got like the motor trip, the overload, and then motor available. Yeah.
Yeah. So my signal power one will be energized, it will open because it's normally closed, right? But this one will close. Then we will need to wait for overload fault to be closed as well to make it motor available, right?
Yeah.
As long as we don't have motor trip.
Yeah.
So all these conditions should be met first to have motor available. Then this will be closed, right? Then I can start my motor. So by pressing this push button here. So let's say that all permissive conditions are met. I press start, so it will close. Motor available already closed because we met the above conditions, considering there is no overload fault and power on. Then it will just trigger this bit to have our motor running. And as you can see, I put some latching here, but in real life, we need to put here actual physical signal, feedback signal, running feedback signal from the motor. It
I
might
think
be.
that's
Mhm.
a good point to mention to everyone. Um, is that some of these are physical, physical on-off signals, and some of them are virtual, like in the memory of
Correct.
the PLC. So,
Correct.
for example, this motor available M14, like that's kind of like a digital signal, but within the PLC. And then we
Correct.
can use that digital signal, that virtual signal within the PLC, and then we can then use that on the rung below where it says again motor available. So it's kind of like a sequence we got. Like if this is true, if these things are true, this is then true, but this is virtual, and then we can use that in the next run here. So if this is true, which might be a virtual thing, it might be a physical thing. We've got this other virtual thing, and this one's true as well. All of these are true, and then it energizes that other rung. Um,
Correct.
so yeah, it's just important to know that some things are actual physical push switches or like auxiliary contacts on a MCB, actual physical components. Other things are like within the memory, like this motor available. acting in
Correct.
the same way, on and off, true or false, but they're virtual.
Yes, correct. So, for example, as you can see, as Chris mentioned, whatever has M, it is a memory bit, which is inside the PLC logic. Yeah. So,
Yes, yeah, M for
what
memory.
yeah, whatever that has I or Q, it is physical. So this is for physical input. This is for physical output. So, for example, overload fault comes as a physical signal. Power on also comes as physical input. But of course, for this case, we will just force them. So just to keep our system running. But whenever we have I or Q, it's a physical signal.
Yeah, so like we got I is like a digital input into the PLC, and then Q is like a relay output, for example, going out of the PLC.
Correct, correct. Yes. So this basically it. One more thing I'd like to mention here. Since we have analog signal, right? So I have two blocks here. So when we talking about analog signal, the PLC sees the analog signal as a raw value, right? So that's why every analog input module has analog to digital converter to convert to bits resolution. You probably have heard about it. So here, as you can see, it's also physical input, but analog input signal because it starts with the I, and it comes in form of integer memory type. So, and here, as you can see, we have min and max, right? Min stands for lower range value, which corresponds to 4 milliampere. And 27,848, it's an upper range value, which corresponds to 20 milliampere.
Yeah, so this is using a 4 to 20 milliamp analog signal.
Correct. Yeah.
Yeah. So yeah, low range. The 4 is the 0, and then the 20 is the 27,648.
Yeah. And why you might be asking why we use this specific range, yeah? So it is just normal operating range for particularly for Siemens software. We also have we have like low saturation, upper saturation, low range value saturation, upper range value saturation. We also have bad PV, yeah, bad process variable, which comes as for example, if we have short circuit or if we have like open circuit, yeah. They also have some values above zero and some values above beyond 27,000. We can use it to configure bad PV, yeah, for analog input signal. But for this, I just use normal operating range to simplify
Okay.
the project.
Did
Yeah.
that I understood half of that. Did anyone else did everyone understand what Alikhan just said there and explained? Or should we
Yep.
did you understand that, Phil?
Yep.
Because
I've
my
I've I've used quite a lot of Siemens and TIA Portal before actually. So I'm used to that Siemens range. It's a weird range because it's not like a 2 to the power of like you'd usually get for like bits and stuff. But yeah, I've had some trouble with that before trying to read in values.
Yeah.
Uh,
I can show here, yeah, about this range. So let me address help section. So it's very useful actually. So we can see this in detail. For example, scaling, yeah. Let's see scaling.
Quick one, guys. If you're looking to upskill in controls and automation and you want more training programs, resources that you can't find here on YouTube and our support, there's a link in the description that will take you to our academy where you can find all of these additional trainings and resources.
Just to when you're finding that, Alikhan, because the half that I understood was like if say like the circuit is broken, like the signal cable is broken, that might read 0 the way it's set up at the moment, and you might not necessarily know whether it's a broken cable or it's just it's a low signal of like 4 milliamps. So with what you were saying, is there a way where you can kind of there's another reading where you can detect whether it's like an open circuit?
Yes, correct. So, so there is a particular raw value, yeah, dedicated to spot the bad PV. Yeah. For example, in case of open circuit, yeah, we have a high resistance, right? That's why our milliampere signal will be very low. It will be below. It will be 0, right? So, and we can have this 0 milliampere to indicate this there is open circuit. The
Yeah.
same for short circuit as well, right? If we have short circuit, it means that our current goes high up. It will be above 20 milliampere. It might be 22 milliampere or something like this. Of course, it is as per NAMUR 43N standard. So it's like it's a it's a standard which used for diagnostic of analog input signals.
Okay. Cool. Thanks.
Most, I don't know about KNX stuff, but most of the Siemens IO modules actually have like a checkbox you can tick in the hardware configuration to detect short circuits and stuff like that, or detect if it's been pulled out. So you can
Yes.
actually set it up and then it'll create an auto alarm. You just assign it to a tag.
Yeah.
Yes, correct. So I'll show you. You're right about this. I'll show you. So, so you can see, yeah, this is our controller and this is analog model, yeah, which comes with 4 analog input, which has 16-bit resolution, yeah. So if I click on this one and click on the properties, okay, yeah. So you can see I can just, for example, channel 1, yeah, we have 4 channels, yeah. So here you can see enable broken wire diagnostics, enable overflow diagnostics. Also here I can set the analog signal. Particularly for this analog input card, we have only 2 type of signals, 0 to 20 milliampere and 4 to 20 milliampere. And 0 to 20 milliampere, I could say that it's becoming obsolete, yeah, because you cannot see the difference between the low range value and open circuit. That's why they use like 4,
Yeah.
4 to 20 milliampere. For example, sorry, or for example, if I put voltage, I can choose range right here, you see? But particularly for this program, we use current because it's much easier and this is what I mostly worked with. So you can just configure each channel individually. For example, you can have this channel as a analog electrical signal which comes in form of current. Next channel you can configure as a voltage. Yeah, it's up to you. For example, if you have like the sensor which works with voltage only or something like this.
Cool. Thanks, Alikhan. That's good.
So where am I? I wanted to show you the 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 range, operating range, but it seems I cannot find it. I can show it later, yeah, if I find it. I will just maybe attach the screenshot to the call, yeah.
Cool. Yeah, that'd be great.
So here, yeah, so we just this function block needs to normalize the volume, so which means that we receive the signal in form of integer and we just convert to real value. Further on, we will use this real value to put into the range that which is understandable for human eye. Yeah, for example, as we said that our temperature range will be from 0 to 100 degree of Celsius, right? So basically what it does, it just converts this raw value into the real. Then this value I can use to put into my operating range, which I will show on HMI. So this value I will use on HMI, and this value will be within this range from 0 to 100. So basically 0 corresponds to 0, 100 corresponds to 27,648. Is it clear?
Yep, makes sense.
Yeah. So the same I did for other transmitters as well, as you can see. So basically, it's that's it in terms of logic. So here is the exciting part, which is HMI visualization. So you want to see? Do you
Yeah.
have any questions regarding this logic?
No questions, guys?
No, I've never worked on this, but I've got an understanding of what Alikhan's saying.
Yeah, sorry if my English is not good. Sometimes, yeah, my English is not my first
Alikhan, I'll bet it's
language.
better than my Russian.
Better than my English.
Sorry,
We're
I just
really interesting.
yeah. Thank you. So okay, let's download this program into the first. Let's compile this program. Let's see if there is any errors. So warning is okay. Yeah, it is most important that we don't have any errors. So I compiled the logic part. Let's download into the PLC simulator. So I don't have a physical PLC. I just use a PLC simulator. So it means that it will just download to simulator. So I downloaded the PLC logic. Now let's go to the HMI. So let's see. So HMI is open. Now I will go to the online mode here. So you see these Googles. So I enter the online mode. Now we can see what is going on here in the logic. So green means that our logic is active. So you see. So in order to simulate and force some signals, I need to use watch table. So here is watching force tables. I will go to the force table because what I need to simulate, force only two digital signals, which is power on and overload fault, and the analog signals. Yeah.
Because these are actual physical things that would be happening in the field. These are like physical inputs that we need to kind of like mimic the operation of, but through the software.
Correct. Yeah. So here, let's see. So okay, let's I remove this one. Yeah, just I will just add again. Yeah. So here we will add power on. Here we will add overload fault. Here I will add also these physical analog signals. Okay. So now, so for example, power on, yeah, as you can see from here, my motor is not available. Yeah, why? Because if we go to this small window, it will show that check main circuit breaker. Yeah. What I need to do, I need to check the main circuit breaker if it is on or off. So since it shows the alarm, check main circuit breaker, I assume that the main circuit breaker is not energized. Yeah. So what we do, we put here 1 or true. It doesn't matter. Yeah. It's a digital discrete signal. So I can put true.
So what
Then,
we've done in the field is we just gone to the circuit breaker and switched it on. That's
yes,
ultimately what we've done.
yes, correct. So this is it's start the force. So I need to once I put some value here, I need to press it here. Then it you see it gives me caution window saying, okay, you're forcing something, like be careful, right? So I'll just yes.
Because sorry to jump in again, Alikhan. Because so what you're doing here is you're kind of overriding potentially any physical things out in the field.
Correct. Yes.
So an example here, guys, might be like, let's say we've got like a pump system with valves and pumps and whatever, like a hydraulic system. What we could potentially, we could cause problems. So like, let's say that we switch on a pump here through the software. We're overriding all the logic, all the controls of the system. We're just forcing things. We start a pump, but we haven't opened up a valve later on in the hydraulic circuit. That pump could be just building up a load of pressure against this closed valve, and it could cause a lot of problems. That's just one example. So that's when you're doing things like this in the software, you've got to be really conscious of what you're actually doing out in the field.
Yes, correct. So as you can see, I forced the power on. Yeah, let's see what happening in the logic. Yeah, so you can see, since I forced this value, I no longer have no power alarm. So let's check the HMI part. So why it is still here? Yeah, I will explain. Because I didn't press acknowledge alarm. So I press acknowledge alarm, it removed. Yeah. So basically, how it happens? Yeah. For example, we have alarm. I first need to press acknowledge, but alarm will stay there unless we reset it, right? Or remove the alarm. In this case, I already removed alarm. The only thing was left to acknowledge, right? So the way of working it is like you first acknowledge, then you deal with the alarm, then you reset, and it will be removed. So as you can see here, we still have motor overload alarm, yeah, and we still have our motor unavailable. Why? Because we have still overload fault. So as you can see here, our overload fault is still present. That's why it generates overload alarm. So in order to complete this circuit, we need to get rid of the overload fault. Then it will close, but it will open. I will show. Oops. Make it true. Let's see what happens. Okay, so as you can see, our motor is available. There is no longer overload alarm. So let's check the HMI. You see our what it says. The status of the motor is available, right? So it was removed. You know why it is just disappeared? Because already I pressed acknowledge before. So let's make it again. Yeah, let's try that there is overload alarm. Yeah. Or maybe let's try that there is power. There is no power. So again, let me just minimize it a little bit so you can see both of them. Yeah. So I also can force from here. I can modify.
Yeah.
So I make 0. So let's see what happens. Okay, looks like I cannot do. Okay, I can do with the memory bit, but I cannot do with the
Yeah.
physical. Yes, correct. So okay, then I need to go to force table. So I will make it. So I will make. So I put here. So the first row is power on. Yeah, I will make it false. I'll put 0. I will send the forcing. So you see, we receive check the main circuit breaker alarm and my motor not available because I removed one of the conditions to make the motor available. So here, what I do, I again make the false for overload fault to show you one thing. So I will make it false. I will force. So it will appear here. You see, as you can see, there is a color code. You see why it is in red and why it is in yellowish. So also you can see. You see there is a letter U and L. So it is alarm class. I just created alarm class. U stands for urgent alarm and low stands for low alarm. So check main circuit breaker we can consider as a low alarm. It's not that urgent. You just need to check the main circuit breaker to see if it is okay or not. But motor overload alarm, it is like urgent because you need to check. Maybe something happened to the motor. That's why it has a different color code. Yeah. So here one thing, I will press the acknowledge first, and you can see that it just changed the color. It means that we acknowledge the alarm. It means that operator already aware of this alarm. That's why when we press the acknowledge, it will change the color. The same for motor overload. I also, as operator, see, okay, motor overload alarm, I need to acknowledge first. It will also change the color. You see? Then, when I rectify the fault, for example, let's put both of them true, it will just disappear because I already acknowledged and I already rectified. Okay? So there is no longer alarm. So okay, our motor is available, and the fun part, what we're gonna do, we're gonna start the motor, right? So I press the start. You see, It's changed from stop to running. Then I can stop the alarm anytime. It stopped. So I again press start push button, and let's say that we have overload fault, yeah. So let's see what happens.
Guys, another quick reminder, if you're an electrician, engineer, and you want to upskill, progress your career, or even advance your business, maybe you're a business owner, and you want some additional trainings, resources, support that you can't find here on YouTube, there's a link in the description that takes you to our academy. You can find all of that stuff there. It's completely free. Yeah, it might help you out.
We have motor overload alarm. We have motor overload indicator here because it was not there yet before. So our motor becomes unavailable and our motor stopped. So is it clear?
Yep.
So what we
Yeah.
do as a technician or a field engineer, we go and see, okay, we check the motor, we see that there is a motor overload. We just press, you know, the on a motor overload relay, we have this reset push button, manual reset push button. It can be auto, it can be manual, but it is probably better to have in a manual mode because it is like gives opportunity to technician or field engineer to check. Then when he makes sure that everything okay, he will just press the reset on the overload relay. Then when he presses reset, we no longer have the overload fault, right? Then our motor again becomes available. Is it okay? Is it clear?
Yeah.
Yeah.
The
So
trip reset button, is that, what's that doing on the HMI?
this trip reset.
Hmm.
So this trip reset is used to reset the trip which is coming from motor winding temperature.
Okay. Okay.
So basically,
Yeah.
we have in industrial, for example, at least in the oil and gas industry area where I work, we have two separate controllers, one for process monitoring and the control, and one for safety system. And there should be two separate controllers. And whatever sensors or final control elements which are responsible for safety will be connected to safety controller. They will have there is like a term known as safety instrumented system, and it will have like multiple safety instrumented functions and so on, which will have like a measuring device, logic solver, and the final control element. And these systems which are responsible for safety will be connected to safety system. But here, since I have only one PLC, I connected both control and the safety to the same controller.
Cool. Makes sense.
Yeah. So let's imitate. Let's imitate that we started our motor. Yeah. Okay, our motor is working, and our motor temperature winding. Our motor winding temperature will rise up. Yeah, as our motor is running.
Guys, I just need to shoot off for 2 minutes. I'll be back. But Alikhan, please continue, mate. Back in a sec.
Yeah, no problem. So here I will give the value in terms of raw value. Remember, from 0 to 27,648. So let's give some random value, yeah? For example, 11,000. So in this value, I give to the temperature transmitter, the first temperature transmitter, which is TIT 101, which is this one, yeah? So once I give this value, So you will see there is some reading. You see 39, right? Let's say that our temperature on a motorbike just starts rising up. I will give the same value to all the transmitters. Sorry. Let me check here. Hmm. Okay, okay. So sorry, here different. It's different tag. I will put the short transmitter. So as you can see, we have the same motor winding temperature, right? So let's say that our temperature is rising up. For example, 15. I will just force it. You see, it changed to 54. So again, I will just change it to 18 maybe. I just want to reach the high alarm state, yeah, for the first transmitter. Okay, a little bit more. 20. A little bit more. Okay, so as you can see, let me first show the temperature itself. So as you can see, our temperature for first temperature transmitter reach its high alarm state, which is equal or greater than 75 degree of Celsius. So now we have 76. So it just changed the color, saying that okay, we have like a high alarm here. And if we go to the alarm window, we can see that TIT high alarm still present here, yeah. Motor overload alarm just you can ignore because we already rectified it, yeah. It will just disappear. But here you see TIT 101 high alarm present. So this alarm corresponds to the high alarm which is coming from first transmitter. But our motor is still running. Why? Because in order to trip our motor, we need to have first high alarm, and the high alarm should come from any two of these three transmitters, right? So let's make a second transmitter to generate. Let's make the second transmitter generate the high alarm. So again, you see, TIT 102 high alarm. We have two high alarms from both transmitters, but our motor is still running because we didn't reach the threshold value of high alarm. So let's make the third transmitter generate the high alarm as well. Okay, so all three transmitters generated the high alarm, but our transmitter, our motor is still running. So let's make the first transmitter to generate high alarm. Let's make it like this. Okay, as you can see, we have TIT 101 high alarm. and it comes as a red color, indicating that we reached the high alarm value. But our motor is still running because we need one more high alarm to trip it. So let's have the high alarm from third transmitter. Yeah? So what happens is, as you can see, we received the high alarm from third transmitter, and we also received motor tripped alarm. So what happened? Motor became unavailable, motor stopped, and motor tripped. Do you remember there was another expression which was healthy, but since it was tripped, it becomes tripped. Motor just stopped. So is it clear?
Yeah, it's to me, mate. Yeah.
So so what happens? What I need to do to reset to have our motor running again. So if I try to trip reset, it will not work, right?
Because the temperatures are still too high.
Yes, correct. So what I need to do as operator, first I need to acknowledge all the alarms. Let's acknowledge one by one, yeah, because it's a good way of doing this. So I acknowledge this operator. What I do, I just try to return the temperature back to high alarm, yeah, to just remove the high alarm. It will be 21,000. So as you can see, we removed the high alarm for temperature transmitter 101, but high alarm for temperature transmitter 101 is still present because we didn't get below the threshold value for high alarm, yeah. So let's make for the third one also. Again, you see? So motor trip is still present. Why? Because I didn't press reset yet. What I do, I press trip reset. My motor becomes available and this becomes healthy. And now I can start the motor again.
Mm. Yeah, makes sense.
So if I acknowledge these ones, it will still be present. Why? Because I still have high alarm for all three transmitters. But if I just remove this, like 18, this also 18, this also 18, it will just reset itself and I no longer have the high alarm. You see? So now our motor is in a nice condition and up and running.
Very good, man.
Yeah.
That's such a nice little project, isn't it? I really like that. Is that how did you come across doing that as a little test project, Alikhan?
Actually, when I used to work as a commissioning engineer, I used to I used to perform safety instrumented system validation, checking all the safety instrumented function, and this is what stuck to my mind. I just try
Right.
to recreate. Yeah, why not recreate that I used to work with? But that time I didn't have a chance to modify the logic because we had like a service engineer who did all the modification and stuff. From my side, it was just suggestion like, okay, it's not working as per control system philosophy. Can you please change? Then I send the like change request. Then they will just process it. If needed, they will just implement. But I didn't have like opportunity to change or modify the logic. That's why I wanted to recreate it and see, okay, wow, it's working, like.
Yeah,
Yeah.
that's brilliant, man. It's yeah. Well, look, guys, it's the end of the hour. Alikhan, mate, thank you so much for putting aside, an hour of your time and sharing this with everyone. Like, I've really enjoyed it. It's been really, really well done. Like, you clearly know what you're doing, and your explanation of all of this has been really, really good. So, thank you, mate.
Okay, that's it for this training. Now look, if you're an electrician, engineer, you want to continue upskilling, we've got a free community with free resources, free support, free training courses that you can't find here on YouTube. The link's in the description and it will take you to our academy. See you on the next video.